Hello guys, this is CodeNCode and this is video lecture for Kosaraju's algorithm for strongly connected component. We have one more lecture, part 1 of Kosaraju's algorithm, where we have studied some of the most important thing that you should have knowledge of before continuing. In this lecture, we are going to see why Kosaraju's algorithm work and the implementation of it, and also we are going to answer one question that we left in the part 1 of Kosaraju's algorithm. And of course, as you can see here, there is some news for uh, students for competitive programming, and that I'll be telling you after the lecture. And so let's continue. So recap to what we have already studied. First, we have already studied that what is transposed graph and the strongly connected the transposed graph and the original graph both have the same strongly connected component. Second, condensation graph, we have already seen that. We have already seen and proved that the acyclic property of condensation graph. We have also proved this fact that out time of Ci is greater than the out time of Cj, where Ci and Cj are two strongly connected component if there is an edge from Ci to Cj. Basically, if there is an edge from A to B, then out time of A would be greater than out time of B, and we have also proved this fact. Now, when we left previous lecture, there was a question and we needed to know what is the order of execution of DFS. How to know that which strongly connected to make call for DFS, or basically which node to make call for DFS, and how to know that which strongly connected component is having 0 in degree. This was the basic question that we left in the previous lecture, and in this lecture we are going to answer that. Now, as you might already know, that Kosaraju's algorithm uses two DFSs. First series of DFS, because it is possible that in one DFS you are not able to cover the whole graph, and the main thing is that you need to cover the whole graph. For if I made a DFS call to any of the node of this strongly connected component, these 4 nodes will not be covered with that DFS call because there is no edge that goes from here to here. So there will be series of DFS calls. Now, so Kosaraju's algorithm uses two different DFS calls. I mean one series of DFS call to identify the order in which the second series of DFS call must be made, and the first series of DFS call tells you the order in which you need to run DFS on the transposed graph to find the strongly connected component. Why is that so? Let me tell you. See, when we left, we know that if we run on the transposed graph, if we run DFS on the strongly connected component which is having 0 in degree, then only the nodes of that strongly connected component will get traversed. For example, this is a graph and this is its condensation graph, right? I have also mentioned their out time of this strongly connected component is 14, out time of this strongly connected component is 9, out time of this strongly connected component is 6. So this is the condensation graph of that, and this is the original graph. Now here you can see this strongly connected component is having 0 in degree. If this is having 0 in degree, then we must make a DFS call. If we make a DFS call to either 5 or 7 or 6 in the transposed graph, then only these 3 nodes will get traversed, and that is our main goal, how to know to which node we need to make DFS call such that only those strongly connected component, only those nodes from that particular strongly connected component gets visited. Basically, each time we need to know which strongly connected component is having 0 in degree, right? Because this strongly connected component is having 0 in degree. If I make DFS call to this strongly connected component in the transposed graph, only this SCC will get traversed, and after that we'll remove it from this graph, and then you see this strongly connected component or this SCC has 0 in degree, and if I made DFS call to this node in the transposed graph, only this would be visited. So after that I'll erase this as well, then I'll be left with only this SCC, and you can make DFS call to any of the node in the transposed graph, and all of these will get visited. So the basic question was the order in which we should make DFS call, how to know which SCC is having 0 in degree. And for that we have this another claim. In the condensation graph, the node which is having the highest out time, these are the out times. In the condensation graph, the node which is the strongly connected component which is having the highest out time is the node with 0 in degree. So the node in the condensation graph of course represent a strongly connected component, right? So if there is a node with the highest out time, then the claim is that then that strongly connected component is having 0 in degree. Now the proof of this is very easy. You can prove it using principle of using contradiction. You can assume, okay, this node is not having 0 in degree, that means there is an edge from some another node towards this. If that is the case, then that node would have higher out time than this, which contradicts the fact that this node is having the highest out time, and hence the assumption that we made that this node is not having 0 in degree is wrong. So this is a straightforward proof. So now we know the node which is having the highest out time is actually the node which is having 0 in degree, or basically that is the strongly connected component which is having the 0 in degree, and that gives us the idea of order of execution. So first we'll make DFS call to that node which is having the the highest out time. In this case it is 7 is having the highest out time, and then when you make a DFS call to 7 in the transpose graph, what would happen? This whole strongly connected component will get visited. So all of these will get visited. Then after 14, the next highest out time is 13, but this is already visited. 12, this is already visited. So 14, 13 and 12, which represent this strongly connected component. After that, the highest out time is 9. 9 represents this strongly connected component, which is actually the strongly connected component which will have 0 in degree after you remove this SCC, which was initially having 0 in degree. So basically we need to run DFS on the transpose graph in the order of high to low out time. But the question is, the ordering of DFS becomes very easy. All you have to do is run a DFS and assign each node its out time. The in time and out time I have already explained in the graph theory series, in the graph theory part 1 series. So if you have no idea how to assign in time and out time for node, you can go and check out that. So after assigning each node the out time, you can sort them by their in the decreasing order of their out time, and then run a DFS on them. How to do that? Let me show you here. So this basically this answers the question that how the first set of DFS actually gives you the order in which you need to run DFS in the second series of DFS. So first, suppose basically I need to sort them in increasing or decreasing order of their out time. In this, the Kosaraju actually sorts the node in increasing order of their time. So from main function, suppose you made a DFS call to node 1. So at time 1 you arrived at node 1, right? From here you made a DFS call to 2, which would have 2 the in time as 2. Now from 2 you would make a DFS call to 3. This would have 3 as in time. Now from 3 you can go to 1, but 1 is already visited, so there's nothing to do. You would leave this node. So basically you are going to leave this. Leaving time or exit time would be 4. Since you are going to leave it, so this would be the first node to leave, right? After that you reach to 2. There's nowhere to go from 2, so you would leave 2 as well. So when you are leaving 2, you are inserting it in the list, and hence this is having the higher time than 3. So basically they are being arranged in the increasing order of their exit time. Now from 2 you would reach 1, and from 1 there is nothing to do, so you would leave 1 as well. So 1 will be inserted in the list as well. Now this SCC has completed. So from main function you would make suppose you made a DFS call to this. So at time 7 you arrived here, so you would leave it at time 8. So when you are leaving it, of course you would insert it in the list as well. After that you made a DFS call to 6. Suppose if you are running a loop from 1 to n and checking whether the ith node is visited or not, and then making a DFS call, then by that logic 5 would have been called, but I'm assuming that DFS call was made to 6. So you are reaching 6. From 6 there is an edge to 7, so you would go to 7 at time 10. From 7 you would go to 5 at time 11. Now there's nothing to do for 5, so 5 would return. Before returning, you would insert it into the ordered list. After that you reach 7. There's nothing to do for 7, so 7 will exit as well, and finally you would exit from 6. So you see, all of these nodes are actually in the order of increasing time, out time, right? And this is the reason why Kosaraju uses 2 DFS. First DFS to initialize the whole list. This is the increasing of order of the out time. The nodes are sorted in increasing order of out time. And how it is done, let me show you. Here, this is AR, which represents the adjacency list. First of all, VI is the vector of int. Let me increase the font a bit. Yeah, VI represents vector of int. Basically it is a list. So AR is the adjacency list for graph, and TR is adjacency list for transposed graph. Now in the main function, what I'm doing, each time reading, there are t test cases. In each test case I'm reading n and m, the number of node, number of edges. After that I'm basically flushing out all of the input from the previous test case, right? So I'm clearing the input from previous test case. After that, reading the edges. So there is an edge from A to B. So in the original graph, in the adjacency list of A, you would insert B. In the transpose graph, this would be a reverse edge. So in the adjacency list of B, you would insert A. So now the construction of graph is completed. Now from 1 to n we are running a loop. So basically we are now constructing this list, the order in which we need to run DFS to find the order in which we should run DFS to find SCCs. So you run a loop from 1 to n. If the ith node is not visited, so of course visited of I would be 0. So we would make a DFS call to that. And what is happening here? Nothing special. You would mark it as visited, and for each node in the adjacency list of current node, you would see whether that node is visited or not, and then you would, if that is not visited, you would make a DFS call. So this is basic DFS stuff. Before returning, you are inserting this node into the list. That is what we were doing here. So when we were returning from certain node, we were inserting them in the ordered list. So this is this represents your order in which the DFS should be executed to find SCCs. After that, what would happen? You would start from here. You would see 6. So you would make a DFS call to node 6. This is the second series of DFS, and this is to find out the strongly connected component. What would happen? You would make a DFS call to node 6. So when you would make a DFS call to node 6, what would happen? 6 would get visited, 7 would get visited, and 5 would get visited. So all of these 3 will get visited. 4 will not get visited because this DFS call will be making on transposed graph, right? So 6 will get visited, 7 will get visited, and 5 will get visited. But from 7 you won't be able to go here because there is a reverse edge. So the edge is from 4 to 7 because we will be running that on transposed graph. So this will get visited. This whole strongly connected component will get visited, right? And then after that you would go to 7 and you would see whether 7 is visited or not, but 7 is already visited. So you would check for 5 is visited or not. Yes, 5 is also visited. After that you will go to 4 and 4 is not visited, so you would make another DFS call. So how many DFS call we have made? 2. First was on 6, second was on 4. After 4 nothing would be accessible from 4 because all of these nodes are already visited, and in the transpose graph there is no edge from 4 to 3. So only 4 will get visited, which is a separate strongly connected component. That is why a successful DFS call was made on 4. After that you would see whether 1 is visited or not. 1 is of course not visited, so you would make a DFS call to 1 and this whole strongly connected component will get visited. After that you will return. So there are 3 successful DFS calls which represent 3 presence of 3 strongly connected component. After that you will see whether 2 can be visited or 2 is visited or not, but 2 is already visited, so you won't make DFS call here. Similarly for 3. So what is happening here, you are running a loop from 1 to n. This REP is a for loop which is done from 1 to n. So I'm starting from the very last node. I'm checking whether the basically n minus ith node. When I is equals to 1, I'm checking for this, and I is equals to 2, I'm checking for this, and so on. So basically I'm starting from last. So if that node is not visited, SCC is a list I'm using to print all of the node of a strongly connected component. Since we are going to find the new strongly connected component, that is why I'm clearing the list from the previous strongly connected component, and then I'm making DFS call to this node, and the DFS1 is being called not DFS. So DFS1 does the exact same thing as this, but this time here we are using transposed graph, not the original graph, and doing the exact same thing. And after that we are inserting the current node in the strongly connected component, because this node is part of the current strongly connected component. And after that what we are doing, we are printing the strongly connected component. Let me show you the code. Let me show you. Let's just run and see whether this works or not. Suppose we have these many test cases. So there are, I guess, 3 3 6 7 nodes, 8 edges. So 1 is connected to 2, 2 is connected to 3, 3 is connected to 1, 4 is connected to 3, 7 is connected to 4, 7 is connected to 5, 5 is connected to 6, 6 is connected to 7. So this is the whole graph, and you see first call was made to node 5. 5 was having the highest out time, so 5 was first we made a DFS call to 5 in the transpose graph, and 6, 7 and 5 are the part of first strongly connected component. I'm also printing the SCC. So 6, 7 and 5, as you can see, are the part of first basically one strongly connected component. After that you would remove that. You don't have to remove actually, because you are marking them visited, right? When you are marking them visited, and when you are running DFS1, you won't run to them because you have already marked them visited, so you can consider them deleted. You don't actually have to delete them. After that the DFS call is made to node 4, because after removing these, the strongly connected component which is having 0 in degree is this strongly connected component. That is why a call to node 4 was made, and in that strongly connected component only node 4 is there. And after removing that, DFS call to node 1 was made, and the strongly connected component contains 1, 2 and 3. And as you can see here, this is the proof that okay, this is working perfectly fine. I'll be providing the code as a reference in the description of the video. So now about the news that I was talking about, that we have for competitive programmers. So the news is this. This is an initiative of Unacademy for competitive programmers. They are launching a new course that you can get a subscription of. The subscriptions are for 1 month, 6 month and 12 month. These are 3 different courses that you can have. And why should you choose this course? Well, there is a very simple reason. These are some of the perks that you will get after you get your subscription for these courses. Now first, of course, you will learn from experts. Now what kind of experts we are talking about here? The best of the best. I'll be telling you one of the instructor that will be teaching you if you of course enroll yourself for these courses for competitive programming courses. And that one guy, I actually idolize him. There are 2 guys I look forward to. Two guys who are ideal for me: Anudeep Nikanti and Tanuj Khattar. I'll be explaining you why I'm telling about these 2, and why I'm telling you that these guys, which will be teaching you if you get the subscription of the courses of competitive programming courses provided by Unacademy. I'll be telling you just in a moment how good they are. Now first thing is that you will be learning from the experts. Second thing, the sessions will be interactive. Of course, you will be able to you will be engaging with the instructors, and you will be able to get your get you any doubts regarding the lecture or the concept that you are studying, algorithm or data structure, whatever you are currently pursuing or currently learning, you will get your answer, you will get your doubts cleared. Third, you have of course structured courses. Now, one of the most common question that I get from my followers is that what is a way, a path that I followed to get better at competitive programming. The path is one of the most important concern. And why is that so? Of course, because if you have a dedicated path, okay, learn this, then learn that, then learn this, and so on. This is the pre-described path. Then you have one thing, that you have assurance that okay, I am improving and this is the path that I should follow. And second thing, you won't waste time. The reason is, suppose you are learning something which already have some requirements which you haven't already studied, and that would waste your time if you do not have idea that okay, I should not learn this first, I should learn this first. There are many times that I've been asked that what path should I follow, should I learn number theory first or graph theory first, or should I practice questions first? So of course there are structured courses that will get you these doubts of yours cleared. And of course when you have subscription, then you have unlimited access of the videos or the lectures, online, offline, for as this all of the courses. You will have subscription access to all of those. You can watch them whenever, wherever you want, on any device you want, of course. So these are these things. Now let me tell you what kind of experts we are talking here. And yeah, there are live free classes going on as well, so you can watch those lectures, free classes, and then after that you can decide whether these guys are worth investing your money or not. So first of all, let me tell you what kind of instructor I'm talking about. These are some of the instructor, but I want you to focus on this guy. Now if you remember, when I uploaded a lecture on centroid decomposition, when I was teaching centroid decomposition, I told you that okay, I'll be teaching you centroid decomposition, which is part of queries on tree lecture series on my channel. So when I was teaching centroid decomposition, I gave you two sources from where you can learn, and I told you that these are the sources where I learned myself, and I told you that these are one of the best sources. And if you remember, this is the article that I gave you link of for centroid decomposition, remember? And this, just see, is written by Tanuj Khattar, the same guy who would be teaching you there in this course if you get a subscription for this course. And just see how good these guys are. This guy is of course ICPC 2020 world finalist, which will be held in Moscow. This Tanuj Khattar himself is world finalist in 2017 and 18, have been worked in Google and Facebook. So you can understand how good their knowledge will be as it comes to algorithms and data structure. These guys are, to be honest, much better than me. I do not know, I don't want to over exaggerate, and I do not know how they will be teaching, but this guy, I actually know how he will be teaching. He will be very good at it because I have read his article. He have been my teacher without even him knowing it. In fact, for this is the first time I'm seeing Tanuj, but I really respect this guy, this and Anudeep Nikanti. So the instructors are really good, and the course that you will be enrolling, there are much more to get in the competitive programming. If you really want to invest your money for good, I think this course should be the first that you should consider for competitive programming. So this was all for this lecture. Thank you guys for listening, and till the next video drops, keep coding. Thank you.